Welcome back to Design a Computer from Scratch. This will be part 9, inserted in the middle because it relates to the processor part itself. There's a couple other appendices that are before this, but it's not always going to be in logical order. Anyhow, in this video we'll look at shifting. I started it in the last video, a little bit of shifting instructions. I'm going to fill that function out and test it in this video. So we did create a shift and rotate instruction. There was some documentation errors in the last video, and it only did logical shifts. So this video is going to add arithmetic shifts, and it will rename the mnemonics for consistency so that they're consistent through their use. It'll be better. And add a couple of new instructions. It's actually going to add 3. One of them's an exclusive OR. Another one will be, and that exclusive OR is what's in a register with an immediate value. There'll be an add immediate to register instruction added, and a compare register to immediate value added, as it says here. And of course the EOR that isn't on here, or the XRI. Okay, changed the mnemonics here for the instructions and added the arithmetic shifts. And I didn't really explain very well in the last video, I think, the encoding of how we get one opcode encoding for all of these shifts and rotates. They're all 0, 0, 1, 1, and they all deal with the register. But those, because that's all you would need to do a shift, is that information. The encoding of the rest of the information about what's being shifted or rotated and whether it's arithmetic or logical is done in the other bits. So the D7 bit shows whether it's a left shift or a right shift. So that's step 0101 because this is left, right, left, right. The D6 bit indicates whether it's a shift or a rotate. So the two shifts are here. Excuse me, 2 shifts are here, and the rotates are here. Well, excuse me, 4 shifts are here, and the 2 rotates are here. And D5, whether it's logical or arithmetic. So the only thing logical or arithmetic count for is shifts. Rotates don't have an arithmetic function because they rotate the least or most significant bit to the other end of the register when the rotate happens. So they are not arithmetic versus logical, they're just shifts. But that D5 will flag that. So we've added the D5, and we've added the shift arithmetic left and shift arithmetic right operation or instruction. These are all encoded by the assembler. It sees SLR, for instance, and makes that 8, 1 in these bits down here. So all of this only takes up one instruction, one 4-bit opcode. Had to add a flag for the logical arithmetic flag into the shifter. Code's a little bit hard to read here, but basically if it's a shift or a rotate instruction, and if left or right, left or right, left or right, and if shift for the first 4, rotate for the second, and then it always only operates currently on account of 1. If you wanted to do a barrel shifter, these could be listed out for however many there are, 8 times 6 instructions. There'd be a lot of lines, but it wouldn't be that tough to do, and the encoding out here would change. But it does show what it does. So if you do a shift left, shift logical left, it will take those 7 bits that were in here and push them up a bit and shove 0 down at the bottom. So this shows what each of the individual types of operations do. I also had to add that flag into the CPU to call that bit, and that just gets connected up to ROM data 5. So that shows the connections, bottom 3 bits going to the shift count. Currently it can only be 0, 1. The bit 5, again, these are all as encoded here, 5, 6, 7. So let's test that operation and use the LAN boards, switches, and LEDs card And we can read the switches to determine which of the operations to run and test each one at a time with that card. That'll shift and rotate a single bit through a register and send it out to the LEDs. So it'll be a visual way of seeing whether it works or not. It was good for debugging. Also add the new add instruction, add the exclusive OR instruction, and add a compare instruction to compare against a constant value, registered against a constant value. The switches are set up to do this. The first switch down here, least significant switch, test the SLL, SLR bits, the next switch, that kind of thing. All the way up to bits, switch 7 will control the add and increment, and switch 8 will test the XOR immediate and compare instructions. Let's dig a little bit into the shift logical left code to see what's going on here. So it starts out by setting the bit pattern as all zeros and a 1 on the far right, and it writes that out to the LEDs. Then it goes down to that routine we have from the previous routine or previous video and does a wait for 1/4 of a second. That's now hard coded, it's not being passed in a register. Then it'll take that register 0, shift it left by 1 bit, and then AND it with FF. If it's shifted all the way over to the left in this operation, because it's in a loop, if it's shifted all the way over to the left, then this will be cleared to 0. So if it's not 0, it'll loop back to loop SLL, which is back up here. So it'll sit in loop, shifting, writing out the bit, waiting 1/4 of a second, and you can look on the LEDs for the card and see that. At the very end of doing one full set, it will then pull again the switches, and if the switch is set for that bit, if all the switches are off, it'll return. I think I changed this to FF because I ended up using all 8 switches, so ignore that when you see it. It should be FF, but it looks at all 8 switches. The next piece of code, very similar. It's a shift logical right. It starts by putting a 1 in that bit and shifts it right and does the same sort of a test here and loops in that inner loop. If it gets down to the bottom here, it reads the switches, and if the switches are all off, if all 8 switches of the switches are off, it jumps back to the starting routine that called all this. Otherwise, it just loops again. Shift arithmetic left is identical in function to a shift logical left, but I'm testing it because it has a different instruction. So the SAL instruction here, and it works. Well, let's see the video and see what it does. Same basic idea. And the shift arithmetic right is a little bit trickier, and we'll see in the video visually how it works. But instead of shifting in a 0, it assumes that the top bit is a sign bit. So if it's a positive number, that would be 0. If it's a negative number, that would be a 1. And the shift just repeats that bit over to the right. But the rest of the code is essentially the same. The test code for rotate the register left is similar to it's very similar to the code for shifting it left, except it doesn't have to reload. It can just run in the loop here, because what a rotate does is it takes that most significant bit. If you're shifting left, it takes what's in the most significant bit and puts it down in the least significant bit, so it'll just keep rotating through all the bits. It doesn't need to be reloaded. So the code is shorter, but it functions differently through the part. The rotate register right code, very similar to the rotate register left code. Again, it doesn't have to test whether you're at the end of the shift or not. It will do on it, it will run for every bit, and because that bit is rotated all the way around, you don't have to reload it. Okay, next one we'll have a little piece of code to test the add instruction, and its mnemonic is ADI, add immediate. We start out by putting 0 into the register for the LEDs, and then we write that out, wait for a quarter of a second, then add 1 to that register 0, and then read the switches to see if we're supposed to end. If we are, return the start, otherwise it jumps back to the loop ADI, which writes out the LEDs. So this will keep counting up, and at a quarter of a second a count with 8 bits of count, that's too long to watch, but let's watch it count for a little bit here. Okay, the final piece of code, which is activated by the far left switch, is to test the exclusive OR and compare. So the exclusive OR instruction is here as XRI, exclusive OR register immediate. This code starts out by writing 55 into register 0 and then putting that out to the LEDs. Then it will wait for a quarter of a second, and it'll do an XOR with FF, which will flip those bits and turn them into AA. Then it writes out that LEDs with the R0, which is the AA, and then it waits for a quarter of a second. Then it compares what was in register 0 to AA to see if the exclusive OR happened. If the exclusive, which is testing the compare instruction, if it did happen, it skips past it if it matched. Otherwise, it'll write out FF. So the pattern we should see should be 55 AA, 55 AA. If we see a 55, the compare failed. Okay, that was a good bit of success. Having an add instruction probably seems basic to a lot of people to have it, but it wasn't there, and now it is, and we can do loop counting and things like that now with it. So that'll be helpful, and you could nest that with using different registers and make much deeper counters if you really wanted to. Since the time is very deterministic and there's no interrupts on this, and it's 4 clocks at 20 nanoseconds per instruction, it would be very easy to calculate what a loop timing would be. Having the exclusive OR gives us the function to be able to invert all the bits or invert an individual bit. And the compare is really identical to exclusive OR. The only difference is it doesn't store the result back into the register like the exclusive OR did. Here we created a branch with our progress so far, and it's up in our GitHub, checked in as part 9_1, and with shift, rotate, EOR, and compare. Thank you very much for watching. Appreciate it. If you like it, please click the like button. Thank you. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindy where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.